Hello everyone, welcome to part 13 module 6 data communication, and this is the last part of this video lecture for this sixth module. So here I am trying to explain this code division multiple access technique. I think this is already came when we studied that multiplexing scheme that time also, but anyway, and this I am trying to explain with respect to that direct sequence spread spectrum. So how that spread spectrum is helping you to achieve multiplexing. Okay, and particularly we call it as CDMA. Already multiplexing technique, frequency division multiplexing and time division multiplexing we already seen, but this is also a way you can try, which is a secure multiplexing scheme. And that is normally, as we already discussed, is used in military applications and all, but at the same time other applications or wireless applications are also using it. So let's see how it is working. Just like so before watching this, you see that previous part. I hope you are coming to this part 13 after completing part 12 only. So that in previous direct when we discussed that sequence spread spectrum, we saw how that spreading is done. The same concept is used here also, but finally we will try to use it for the multiplexing way. So CDMA is a multiplexing technique used with the spread spectrum. The scheme works in the following manner. We start with a data signal with a rate, say D bits per second, something like that. So which we call the bit data rate of the input. So each bit is now broken into k chips according to a fixed pattern that is specific to the particular user who is trying to send the information. That we already seen, like we have using that pseudo random number generator, we generate a spreading code, and using that spreading code we will do some kind of XOR operation or something. As a result, it will be generated. We are getting a feel like the particular bit is being broken into, say, k chips, in the sense k is the length of the spreading code being generated by the particular user who is trying to communicate. Okay, so the new channel has a chip data rate. As a result, the original bit rate is D, that will be now multiplied by k, because instead of sending a single bit, now we are sending k bit on the same position as that of a single bit. So the data rate of the resultant signal after doing the spreading will be k times D, say chips per second. Now we are using the term. D is bits per second. Now k into D is actually not bits, right? Because the original single bit you are dividing into say k parts, and each part we call as a chip. Okay, so this k into D is the data rate. You can use the unit chips per second for that. As an example, let's see, let's take that k is equal to 6. It is simplest to characterize a code as a sequence of ones and minus ones. Just like we already seen, instead of 1 and 0, here 1 and minus 1 we are using. Okay, for 0 minus 1 is used. This figure shows the codes for 3 users A, B, C, each of which is communicating with the same base station receiver, R. So it assume a situation 3 user A, B, C, and all the 3 are communicating with the same receiver R using a common shared medium, right? And that is where the multiplexing is done. Now we are going to see how this multiplexing is achieved. And for that, each of the user is given a chipping code, okay, and that is nothing but the pseudo random noise being generated by the pseudo random number generator. So let the chipping code for A be 1 minus 1 minus 1. This is something randomly generated, some 6-bit code. Okay, instead of 0 here minus 1 is used. Similarly for CB, let it be, and for the user C, the chipping code for user C, that is denoted by capital C and small c. Capital C for chipping code, C is the small c is the user identification. Okay, C A C B C C, like that 3 chipping code. Just we are taking as an example. This is something randomly generated only. And anyway, not only the case, the receiver should be knowing also, like if the information is coming from A, this is a chipping code. If it is from B, this is a chipping code. That is already communicated with the receiver also. Then only it will work. Now this is the case. Suppose a message to be communicated be 1101, and it will be encoded like this. If it is sent by A, each bit, say 1, will be encoded using this chipping sequence. Now the single bit is now represented by a 6-bit or 6 chips, something like that. So if the original data reaches some d bits per second, after that it will be some 6 times d chips per second, like that. Okay, so here it is represented by a 6-bit code, and as it is 1, it is simply represented as it is. when it is 0 is coming, its complement will be coming, because that XOR operation we are doing on the background. Okay. Okay. So this is the way we are representing. I am not sure whether it is XOR operation, but anyway, or it's complement of that, whatever it is. Simply we have to differentiate. So when 1 is coming, so it is represented by the same chipping sequence, and for 0 it is differentiating and 0 from 1 by using complement of that. Okay, you see what is the operation done on the background. Now when it comes to user B, he has a different chipping code, and using that chipping code the information is being represented like this. Now okay, just that chipping code is being it is not like what we see in DSS. Simply just we are understand like this, 1 and 0 are this, we can differentiate each other. For 1 just repeat the chipping code as it is, and for 0 just take its complement. Same thing happening at B, and similarly same thing happening at C, and these 3 codes are different. Now consider the case of user A communicating with the base station A, B, C, all the 3 can communicate, and for the time being, suppose A is communicating in the base station, and assume that the base station is knowing A's code, then only we can implement this. So for simplicity, we assume that the communication is already synchronized, so that the base station knows when to look for the codes. Okay, and there will be some kind of synchronization mechanism by which the receiver will be knowing that it is I mean, whenever some information is coming, that time only the receiver has to tune to the medium, right? Otherwise, if nobody is sending some information, it don't have to tune to the media. And for that time, and how it is understanding that some information is coming, that is by means of some special synchronization bit. Synchronization also we seen. Suppose that such a synchronization scheme is being implemented, and by looking at the synchronization bit, say start of a frame or start of some communication is being indicated by some special sequence, and by looking at that sequence, now the receiver is tuned with the medium, and now it is say it is trying to decode the information as it is being sent by A, but as it is multiplexed, if B is also sending, that also may be there in the transition medium, that we don't know. But our requirement is when the receiver is receiving the information by thinking that it is from A, if it is actually getting some information from B or C, it should be able to discard it, and it should selectively accept the information that is being sent by A alone. And let's see how it is done. Suppose A wants to send 1 bit, then the pattern will be sent as it is. That is what I explained in the previous figure. If it want to send 0, its inversion will be communicated. Just this one, its complement will be communicated, right? So the base station on the receiver decodes the chip pattern, and how this decoding is done. When I tried this animation here, I find some difficulty. That is why I listed like this. Just look at the mouse arrow movement. So in our simple version, if the receiver R receives a chip pattern, so this is the pattern being received by the receiver D1 D2, that 6 bit in the sense now we call as 6 chips, right, per bit, like that, whatever it is. This is being received by the receiver and seeking to communicate to the user U is a particular user. So this is a general representation of the decoding process, and let the user use code B. Okay, like A, B, C, we already seen 3 different codes. Suppose in general this is a code used by a particular user U. Then what the receiver will be doing, it perform the following decoding function, and it will be simply multiplication of the bits together and adding up them together. So this is one way. You can try different ways also. This is the one being explained in your textbook. So simply that multiplication addition process corresponding like a C1 into D1 plus C2 into D2, like that it will be done at the receiver. Now see how it is going to help the decoding process, whether the receiver is able to decode that original information exactly as it is. Now suppose see D is the information being received by the receiver, and U is the user who sent the information. So suppose A sends a bit pattern something like this, not something, this is the one we taken as an example. This is a bit pattern of A. I mean chipping code of A. If A is sending bit 1, then this chipping code will be sent as it is. If A is sending bit 0, then its complement will be sent by A, right? That something we already see. Now suppose the receiver is receiving this pattern. That means the user A is sending a binary 1. After doing that spreading, this binary 1 will be sent like this pattern. Okay, and suppose the receiver correctly received that pattern. Now what the receiver will do is, whenever it is receiving this, it will try to decode this information using the chip code of A. So the chip code of A is already communicated to the receiver, right? So chip code of A and the information being received, both are same. So simply 1 into 1 minus 1 into minus so some printing mistake is here, sorry. This is just like 1 into 1, then minus 1 into minus 1. Okay, this one is something I forgot to delete. Okay, sorry, this one is not there. Minus 1 into minus 1, again minus 1 into minus 1, and 1 into 1, minus 1 into minus 1. So every bit is multiplied with itself, in the sense the information being received by the receiver is this one, and A's chipping code is also this one. And as it is sending the binary 1, the same pattern will be sent by this by A, right? So what is the result of doing this operation? You can just calculate this. You will be seeing that it is 6. You are getting the simply 1 into 1, minus 1 into minus 1, again 1, minus 1 into minus 1, all are 1, 6 ones add up to 6. Now suppose a sender is sending, I mean A is sending 0, so that this is the original pattern. Its complement will be sent by A, right? That is minus 1 1, just its complement, and it is being received by the receiver. Now the receiver will be decoding this received information using A's chipping code, and A's chipping code actually this complement of this. So when you are multiplying this minus 1 into 1, every bit will be just multiplied with its complement. You will be getting the result as minus 6. So if A is sending 1, the receiver will be decoding that 1 as 6. If A is sending 0, the receiver will be decoding it as minus 6 using A's chipping code, right? Now suppose it is trying to if someone else is sending the information, and when it is suppose instead of A's information, suppose the receiver received B's information, because as it is multiplexed medium, in others data will also come, right? And that time the receiver, when it is trying to decode using A's chipping code, it will be getting the result something different than the 6 and minus 6. So the idea is like this. So not that it is always a case that if the receiver is decoding the information using A's chipping code, right? So you have to interpret like this. So D is information being received by the receiver. It can be sent by A or it can be sent by someone else. But as it is decoding it using A's chipping code, no matter what the sequence of minus 1s and 1s are received, that the only D's result in the extreme value. So it will always result in minus 6 to 6 if it is being sent by A. But if it is receiving information from some other source, you will be getting a value different from this minus 6 and 6. So this is the extreme value that is possible. So it is like this. The SA, that is when the receiver is decoding using A's chipping code, it will generate plus 6. We say that we received 1 from A, right? And minus 6, we say that we received a 0 from A. Otherwise, we assume that someone else is sending the information, or it could be some error. So this is how we are handling that multiplexing and error all situations. So now what happens if user B is sending and we try to receive it using A's chipping code? Let's see, like this is when B is sending 1, it will be sent with B's chipping code, something like this. And when the receiver is trying to decode it using A's chipping code, the result is 0. So we just cross check. The code is something fixed that we fixed in the beginning of our discussion: A's code, B's code, and C's code. So as B is sending 1, it will be sent as its chipping code as it is. And when it is decoded using A's chipping code, okay, so here the other one bit is from this, other bit is taken from A's chipping code. You cross check with it, and the result you obtained is 0. Similarly, the other case 0 also, something like that will happen. So the unwanted signal from B does not show up at all. You can also verify that if B is sending 0, so that its complement will be sent by B, right? And the decoder would produce a value of 0 for SA again. That means if it is receiving information from A, definitely it will be decoding it to a value from -6 to 6, -6 for 0 and 6 for 1. If it is after doing this decoding function, if the result is 0, it can directly conclude that it is an information that is being sent by some other user which I am not interested for the time being, because at any time the receiver can tune to a particular user, right? If it is tuned to A, it want information from A, but in somehow due to error or some other reason, if some other information is being coming, it will correctly be it means identified by the receiver, and the unwanted signal will not show up at all, because it will be getting the 0 as a result. Okay, so the basic principles are like this. So this is something, an important concept. Just listen to this. So this means that if the decoder is linear, you know what is linear function in mathematics? It's something like this. When you apply a function over a polynomial like this, if you can means SA of SA plus SB, if you can just expand it like this, SA of SA plus SA of SB, if it is expandable like this, such functions are called linear. Okay, so assume that the signal, the decoder is linear, and if A and B transmit the signal, so SA and SB are the signal being transmitted by A and B respectively at the same time. And you know, as it is multiplexing, A's data and B's data will be combined and it will be coming together. So the receiver will be receiving it as a single signal, which is a combination of SA plus SB, but now the receiver will be correctly able to decode SA alone, because of the property that we seen already, that is like the signal that is SA plus SB that is received by the receiver is the receiver is now trying to decode that signal using A's chipping code. Okay, so this A means the receiver is right now the receiver is willing to take information from A only, so it will be decoding it using A's chipping code, and this is what is being received by the receiver. So SA is a pattern being sent by A using, it can be 1 or 0. If it is 1, its chip code will be sent as it is. If it is 0, its complement will be sent. Similarly for B, whatever it is, and the combined signal is being received by the receiver, and the receiver is trying to decode it using A's chipping code. So that as the function is linear, you can expand like this, SA of SA plus SA of SB, and now this will be SA of SA, because this part is simply 0, like that is what we seen in the previous slide. Like when the receiver is decoding the information being received from B using A's chipping code, the output is 0. Then there is no confusion at all. Simply you can ignore this term and it will be interpreting only A's information. So even though it is a combined one, if it is A's alone, it will be interpreted as it is. If it is multiplexed together and A's and B's data together, correctly the receiver is now able to tune to A's data alone, even though it is combined with the B's data. So since the decoder simply ignore B when it is using A's chipping code. Okay, or means ignored in the sense you after this calculation is resulting you 0. So that is a very important feature, and such chipping codes having this property, that means when you are means decoding it using someone else chipping code, you are getting the result as 0, then it is very easy to filter out, right? Such chipping codes are said to have the property orthogonality. So if A and B that have the property that when you decode B's encoded data using A's chipping code, or when you decode A's encoded data using B's chipping code, if the result is 0, then you can say that A and B are orthogonal to each other. So this orthogonality is very important when you are forming a chipping code like this. Suppose 3 users want to communicate in this way, A, B, C, then this pairwise orthogonality is ideal. Okay, like A and B orthogonal each other, B and C orthogonal each other, A and C also orthogonal each other. But you know, practically when you are designing such multiplexing scheme, it is somewhat difficult for you to achieve this orthogonality. So orthogonality in the sense exactly the other combination, it should result to 0. But if even though it is not 0, if you are getting a value that is very smaller, like some 2, 1, something near to 0, that is also acceptable, because in practical case it is difficult to get a perfectly orthogonal code like this. So such codes are very nice to have, but there are not all that many of them. We don't have that many options. So more common thing is that because as when we are not able to produce such a orthogonal code, because this is a case with three user, some AB, BC, AC, like that. In that three pairs we need orthogonality, but when it comes to number of users is increasing, that pairs of orthogonality requirement will be more and more, and that time it may not be possible for you to make all these pairs orthogonal each other, and that time what you can think as an alternative or the common strategy that we are using is this when you are decoding Y's code using X chipping code, some X and Y, just like this, even though you are not getting 0, some small value, some absolute value you are taking, just like instead of 0, if you are getting say 1 and minus 1, it is fine. 2 and minus 2, it is fine, because in the actual case you are getting some 6 and minus 6, right? So the absolute value, very small absolute value is also preferred when the this X and Y are not equal to each other, and S of X and it is trying to decode using someone else chipping code. So then it is easy to distinguish between the two cases, whether it is X equal to Y and when X not equal to Y. So in our example, it is like if you are checking that you can cross check, like we already seen the case when you are decoding the B's data using A's chipping code, you are getting 0. That means the orthogonality is maintained between A and B. A and B orthogonality is maintained, that we verified already. Now if you cross check it again, you can see that A and C also that orthogonality is maintained. That means you take the information being sent by C, 1 or 0, whatever it is, and you try to decode using A's chipping code, and similarly A's data you decode using C's chipping code, you will be getting the result as 0, but between B and C it is failed to maintain that orthogonality. But instead of getting 0, we are getting a small value, that is also fine. The absolute value is small, like 2, that is also fine. So in the later case, the C signal would make a small contribution to the decoded signal instead of 0. 0 it is very easy for you to eliminate, but when it is coming like a very small value, you can filter, or it will be there in the signal being received by the receiver as a very small noise. So using the decoder SU, the receiver can sort out the transmission from U even when there may be other users broadcasting in the same cell. So somehow it can sort out that issue. The CDMA receiver can filter out the contribution from unwanted users, or they may appear as a very low level noise. So that just for your calculation, you can cross check the table I just taken from the textbook only. You verify that, just take those 3 codes and you see whether orthogonality is maintained between all the pairs, and see how when that correct decoding is done. Some of the calculations is shown here, like 6 minus 6, that is something we already explained, and maybe from B and A is trying to receive, you are getting as 0. From C, when between C and B orthogonality is not maintained, but you are getting a very small value like 2, and those calculations were shown here that you can verify in your own way. So hope you get an idea about how this chord division multiplexing is working, how the signals are being multiplexed simply by spreading it over using some sequence, and that demultiplexing is done correctly because of this orthogonality property or something like this. Okay, thank you. With this we are winding up our discussion on module 6. So I wish all of you to score very good mark in your exam. I tried to cover maximum, other than very few topics which I given you as assignment, most of the important topics, not only important, from your syllabus point of view, I covered almost all topics. Okay, thank you.